Welcome to PRAMODH's Code Crafter. I'm excited to introduce you to the fascinating concept of the Internet of Things. Today, we'll be diving deep into a mini project that explores the various topologies used in IoT networks through Python simulations. Let's get started. Before we continue, I would like to take a moment to express my sincere gratitude to my exceptional Internet of Things professor. Your guidance, enthusiasm, and unwavering support have been instrumental in my success throughout this project. Your passion for the subject was contagious, and your ability to break down complex concepts into easily understandable terms made learning a joy. I am truly grateful for the knowledge and skills I have gained under your mentorship. I would also like to thank the entire CSE department of my college for providing me with the resources and opportunities to pursue this project. Your commitment to fostering a learning environment that encourages innovation and creativity is truly inspiring. Finally, I want to acknowledge the contributions of my peers and colleagues. Their feedback, support, and collaboration have been invaluable in shaping this project. I am fortunate to have had the opportunity to work with such talented individuals. Thank you all once again for your support and encouragement. I am truly honored to have been a part of this journey. Welcome back. As we delve deeper into the world of IoT, it's essential to understand the underlying structure of these networks. This structure, known as network topology, significantly impacts how devices communicate and data flows. Today, we'll be exploring different IoT network topologies and simulating their behavior using Python. By comparing these topologies, we'll gain valuable insights into their advantages, disadvantages, and suitability for various IoT applications. Let's start by examining the different types of network topologies. Now that we understand the basics of network topologies, let's outline the specific goals of our project. Our primary objective is to simulate various IoT network topologies. We'll use Python programming to create virtual models of these topologies, allowing us to experiment and observe their behavior in different scenarios. Secondly, we'll visualize these topologies. Using Python libraries, we'll create visual representations of each topology, making it easier to understand their structure and how devices are connected. Finally, we'll analyze the performance of these topologies. We'll evaluate their efficiency, reliability, and fault tolerance. This will help us determine which topologies are best suited for different IoT applications. By achieving these objectives, we'll gain valuable insights into the strengths and weaknesses of different network topologies, enabling us to design more effective and reliable IoT systems. Starting off with the star topology. As we begin our exploration of IoT network topologies, let's set our sights on the star topology. In this configuration, devices, often called end devices, connect directly to a central hub or coordinator. This central node acts as a central point of communication, managing data flow and information exchange between devices. The star topology is a popular choice for many IoT applications due to its simplicity and ease of management. Let's delve deeper into its advantages and considerations as we progress through the presentation. Continuing our exploration of IoT network topologies, let's move on to the mesh topology. Unlike the star topology, where devices connect directly to a central hub, the mesh topology forms a network where devices are interconnected with multiple paths. This creates a more resilient and fault-tolerant system, as there are multiple routes for data to travel. Key characteristics of the mesh topology include hierarchical structure. Devices are organized in a hierarchical manner, with some acting as parent nodes and others as child nodes. Scalability. The mesh topology can easily accommodate additional devices, making it suitable for large-scale IoT deployments. Dependency on intermediary nodes. While the mesh topology offers redundancy, it relies on intermediary nodes to facilitate communication between devices. Common applications of the mesh topology include corporate networks. Departments can be organized in a hierarchical structure, with each department connected to multiple others. Smart agriculture. Sensors can be deployed throughout a field, forming a mesh network to collect data for precision farming. By understanding the mesh topology, we can appreciate its benefits and potential drawbacks in various IoT scenarios. Continuing our exploration of IoT network topologies, let's delve into the tree topology. The tree topology is similar to the mesh topology in that it also employs a hierarchical structure. However, in the tree topology, each node connects to only one parent node, creating a more centralized and structured network. Key characteristics of the tree topology include hierarchical structure. Devices are organized in a tree-like fashion, with a root node at the top and branches extending downwards. Scalability. The tree topology can be expanded by adding more branches and nodes, making it suitable for large-scale IoT deployments. Dependency on root node. The root node plays a critical role in managing communication and data flow, making it a single point of failure. Common applications of the tree topology include corporate networks. Departments can be organized in a hierarchical structure, with the root node representing the central management team. Smart cities. Sensors and devices can be deployed in a tree-like structure to monitor various aspects of urban environments. By understanding the tree topology, we can appreciate its advantages and limitations in different IoT scenarios. Continuing our exploration of IoT network topologies, let's discuss the bus topology. The bus topology is a simple and cost-effective network structure where all devices are connected to a single shared communication line. This line acts as a highway, allowing devices to transmit and receive data. Key characteristics of the bus topology include shared communication line. All devices share a single cable or bus for communication. Simplicity and cost-effectiveness. The bus topology is easy to implement and requires minimal cabling. Prone to collisions. Since all devices share the same channel, there's a risk of collisions occurring when multiple devices attempt to transmit data simultaneously. Common applications of the bus topology include vehicle IoT networks. Sensors and actuators in a vehicle can be connected using a bus topology to share data and control functions. Home IoT networks. Basic communication lines for connecting devices like smart lights, thermostats, and security systems can be implemented using a bus topology. While the bus topology offers simplicity and cost-effectiveness, its susceptibility to collisions can limit its performance in certain scenarios. Therefore, it's important to carefully consider the specific requirements of your IoT application before selecting the bus topology. Our final topology for today is the ring topology. In a ring topology, devices are connected in a circular fashion, forming a closed loop. Data travels in a single direction around the ring, passing through each device until it reaches its intended destination. Key characteristics of the ring topology include circular connection. Devices are arranged in a circular configuration. Data movement in one direction. Data travels in a clockwise or counterclockwise direction around the ring. Fault tolerance. A fault in one node can disrupt the entire network unless a dual-ring configuration is used. In a dual-ring topology, there are two interconnected rings, providing redundancy and fault tolerance. Common applications of the ring topology include city surveillance networks. Cameras and sensors can be connected in a ring topology to monitor city streets and public spaces. Industrial systems. Pipelines and grids can be monitored using sensors connected in a ring topology to detect anomalies and ensure efficient operation. By understanding the ring topology, we can appreciate its advantages and limitations in various IoT scenarios. Now that we've explored different network topologies, let's outline the steps involved in our project. First, we'll define the network topology. This involves understanding the characteristics and requirements of our IoT application to select the most suitable topology. Next, we'll select the specific network topology. Based on our analysis, we'll choose one of the topologies we've discussed, such as star, mesh, tree, bus, or ring. Once we've selected the topology, we'll implement it in Python using the NetworkX library. This library provides powerful tools for creating and analyzing network graphs. To visualize the simulated topologies, we'll use both NetworkX and Matplotlib. These libraries will help us create clear and informative visualizations of the network structures. Finally, we'll analyze the results. By comparing the performance of different topologies, we'll be able to identify their strengths, weaknesses, and suitability for various IoT applications. This flowchart provides a clear overview of our project's workflow, ensuring that we follow a structured approach to achieve our objectives. Now that we have a solid understanding of network topologies, let's dive into the practical implementation using Python. In this slide, we have a code example demonstrating how to create and visualize a star topology. We'll be using two powerful libraries. NetworkX. This library provides functions for creating, manipulating, and analyzing network graphs. Matplotlib. We'll use Matplotlib to visualize the created network topology. The code snippet shows the steps involved in importing necessary libraries, importing NetworkX and Matplotlib, creating a star topology, using NetworkX functions to create a graph with a central node and multiple connected nodes, drawing the topology, using Matplotlib to visualize the created graph, including nodes and edges, adding labels and titles, adding labels to nodes and a title to the visualization, displaying the plot, showing the final visualization. By following these steps, we can effectively simulate and visualize various network topologies in Python. In the upcoming slides, we'll explore the code for other topologies and discuss the analysis process. Now that we've simulated and visualized various network topologies, let's analyze the results and discuss their key characteristics. Starting with the star topology, we found that it offers efficient communication, but its centralized structure makes it vulnerable to failure if the central hub goes down. On the other hand, the mesh topology demonstrates excellent fault tolerance due to its redundant connections. However, its complex structure can increase implementation and maintenance costs. The tree topology is scalable and can accommodate large networks, but it relies heavily on parent nodes. If a parent node fails, it can impact the performance of connected child nodes. The bus topology is simple and cost-effective, but its shared communication line can lead to collisions, reducing overall performance. Finally, the ring topology offers consistent performance and can be relatively fault-tolerant with the use of dual rings. However, it can be susceptible to failure if a single node malfunctions. To summarize, the choice of network topology depends on the specific requirements of your IoT application. Factors such as scalability, fault tolerance, and complexity should be carefully considered when making a decision. Let's take a closer look at this bar graph to visually compare the fault tolerance and complexity of each topology. Now that we've analyzed the characteristics of different network topologies, let's explore some real-world IoT applications and how these topologies can be utilized. Smart cities are increasingly relying on IoT technologies to improve efficiency and sustainability. Mesh topologies are particularly well-suited for applications like smart grids and traffic systems, as they offer resilience and scalability. In the healthcare domain, IoT devices are being used to monitor patient health and improve medical care. Star topologies are often used in centralized device management systems, providing a centralized hub for data collection and analysis. Smart agriculture is another area where IoT is making a significant impact. Tree topologies can be used to create sensor networks that collect data from various locations in a field, enabling farmers to make informed decisions based on real-time information. These are just a few examples of how different network topologies can be applied to real-world IoT applications. By carefully considering the specific requirements of your project, you can select the most appropriate topology to ensure optimal performance and reliability. As we conclude our exploration of IoT network topologies, let's discuss some potential future implementations that can further enhance the capabilities of these systems. Dynamic node handling is a crucial feature for IoT networks, allowing for the seamless addition or removal of devices without disrupting the network's operation. This is particularly important in scenarios where the number of devices in a network is constantly changing. Hybrid networks offer the flexibility to combine different topologies to address specific requirements. For example, a hybrid network might incorporate a mesh topology for fault tolerance and a star topology for centralized management. Edge computing is another emerging trend in IoT. By processing data closer to the source, edge computing can reduce latency and improve responsiveness, making it suitable for real-time applications. Finally, security is a paramount concern in IoT systems. Implementing robust security protocols is essential to protect sensitive data and prevent unauthorized access. This includes measures like encryption, authentication, and intrusion detection. By exploring these future implementations, we can envision the continued evolution of IoT network topologies and their potential to revolutionize various industries. In conclusion, we have successfully simulated and visualized multiple IoT network topologies, gaining valuable insights into their characteristics and performance. Through our analysis, we have identified the strengths and limitations of each topology. This knowledge will help us make informed decisions when designing and implementing IoT systems. Looking ahead, there is significant potential for future developments to optimize IoT networks. Areas such as dynamic node handling, hybrid networks, edge computing, and advanced security protocols can further enhance the capabilities and reliability of IoT systems. As IoT continues to evolve, it's essential to stay updated on the latest trends and technologies to ensure that our networks remain efficient, scalable, and secure. Thank you for your attention. Thank you all for your attention. I hope this presentation has provided you with a valuable understanding of IoT network topologies and their applications. If you have any questions or would like to discuss specific topics further, please don't hesitate to ask. I'm happy to clarify any points or provide additional information. Feel free to contact me through the comment section of this YouTube video. I'll do my best to respond to your inquiries promptly. Once again, thank you for your time and interest. I look forward to continuing the conversation and exploring the exciting world of IoT together.